In this video, we will derive the equations for pressure and density for the International Standard Atmosphere. Remember the two equations which we derived the last time, the equation of state, and we added to it the hydrostatic equation. These two equations are the starting point of our derivation, and especially the lower one. The hydrostatic equation dP equals minus rho g dH. Here we have the change in pressure, but we also have the density here on the right side, and we have the dH, so this is not yet something which we can work with. We're mainly interested in the pressure change. So let's first use the equation of state to get rid of the density and change it into pressure. Pressure equals rho RT, which means that the density equals the pressure divided by RT. So if we now substitute the rho into the hydrostatic equation, we get dP equals minus P divided by RT g dH. Now, the next step is to make sure that the pressures are all on the left side of the equation. So we divide left and right by the pressure, which gives us 1 divided by P times dP, and here we get minus g RT times dH. Well, the left side now looks okay. This is an integral which we can solve. But on the right side, we see that we still have the temperature, which will vary. The R and the G will remain constant, but we have the dH here. So we're looking for the relation between temperature and altitude here. Well, from the graph, we saw that the temperature changes linearly, which means that we can write the temperature at any altitude 1 equals a starting temperature plus the temperature gradient times the difference in altitude. And this is called the formula of Toussaint, which gives the temperature as a function of altitude. So, as we said, we start with the temperature. This character A is the lapse rate, or temperature gradient, and it's given in Kelvin per meter, and it indicates a change of temperature per change in altitude. In other words, dt divided by dH. We can also write this as dH equals dt divided by A. And this is useful for our equation because by filling in this equation for the dH, we get much closer to something we can solve. 1 divided by P times dP remains unchanged. Here we get minus G R times 1 divided by T times dt divided by A. And we can write this in a different order because we have a number of constants here on the right side. We have this is now a constant, this is a constant, and this is a constant. The t will vary. We have a dt behind it. So this is true for a very small step. For a very small step in altitude, this is true. But we want to make a larger step, and therefore we have to make this into an integral. So this means we will jump from an altitude 0, where we have a pressure 0, to an altitude 1, where we have a pressure 1. And here we have the constants, which we can put in front of the integral, times the integral t0, t1, 1 divided by t dt. Well, this becomes high school mathematics now. On the left and right side we see the same integral, and the solution to the integral 1 over p is the natural logarithm of p, which means we can write this integral as the natural logarithm of p1 minus the natural logarithm of p0 is the same as g divided by ar times, again, the natural logarithms, but now for temperature. Basically, we're done now. We have an equation which would work if we have a start value for P0 and a temperature T0 with which we can calculate the T1. We know A, we know G, we know R. We could calculate P1. But we can make this into a much neater equation because we want to get rid of this logarithms. The natural logarithm. How do you get rid of a logarithm? In this case, by using e and raising it to the power of this equation. So this means we get e to the power ln p1 minus ln p0 equals e to the power, and then the whole right side of the equation, g divided by ar minus the logarithms for temperature. And now we need to use two computational tricks which should be familiar to you, and that's with powers. Remember, we can always say that we have x raised to the power a minus b, that's the same as x to the power a divided by x to the power b. And similarly, we can also say x to the power a times b is the same as x to the power a raised to the power b. And these two tricks are what we will use to make this even simpler, this equation. So minus means dividing, so this is the same as e to the power ln p1 divided by ln p0, which is the same as e to the power ln t1 minus t0 minus ln t0. Still readable? No, barely, but sufficiently. Raised to the power minus g divided by ar. Now this we can really simplify. Here e to the power of the natural logarithm becomes p1 divided over p0. And here, on this side of the equation, the same happens, and this becomes t1 over t0, resulting in the equation p1 divided by p0 equals t1 divided by t0 to the power minus jar. And we got rid of the logarithms. Of course, we still need to know the relation for density. Let's go to the next screen for that. So we have p1 divided by p0 is t1 divided by t0 to the power minus jar. And we want to change this into density. Well, we know with the equation of state that P equals rho RT. So let's substitute this, and this means that it becomes rho 1 R T1 divided by rho 0 R T0. This is the same as P1 over P0, and on the right side of the equation everything remains unchanged. Well, let's look at this equation. The R disappears, and this is something we can divide out of the left side, which means we'll get rho 1 over rho 0. But we also have to divide the right side by the T1, T0, which means reducing the power with 1. And this now is our second equation for a layer with the temperature gradient. This is the first one. And these two equations give for large steps the new pressure and new density. So you use this by filling in the base layer of the layer values for 0. You can calculate any target altitude which are indicated by the index 1. There is, however, one problem. There were some layers where the actual value of the lapse rate was equal to 0. And in our situation, this will not work. Here, these equations will only work if the lapse rate is not equal to 0. What does this mean? A lapse rate not equal to 0 means there's a temperature gradient, so the temperature changes. If it's equal to 0, we have a layer with constant temperature, and this is also called an isothermal layer. And we saw a few of those in the previous video. What happens if we would use these equations with the lapse rate 0? We divide by 0. And that, of course, is not allowed. So even though these are good equations for any layer with a lapse rate which doesn't equal 0, we need an additional set of equations for the layers with a constant temperature. Well, let's step back and see where we went wrong. Here, top of the screen, we already were dividing by the lapse rate. Even further back, here we're still okay, the beginning of the equation, and then here is basically where we start assuming that the lapse rate is not equal to 0. So that means that we can use this equation as the start for the equation of the isothermal layer. So let's see if I remember this correctly. Which equation did we have? We had 1 over P dP equals minus G over RT times dH. Here we're still okay. And in a way it has now become much simpler because basically T1 is equal to T0 is T is constant. So this means that this whole set here is now constant. And that makes life much easier. So on the left side, everything stays the same. So if we make it into an integral, and here we do the same. The right side remains the same. ln P1 minus ln P0 is how we solve that integral. But here we can take the constant in front of the integral, and this merely becomes the altitude difference. Basically, we're solving the integral 1 as the function for h, which becomes h, and that means we can fill in the altitude difference. Now, to get rid again of the natural logarithms on the left side, we raise it to the power. So we do the same trick basically. E to the power ln P1 divided by e to the power ln P0, identical to the temperature gradient layer. And on the right side, we get a different power. No logarithms here, which means that in this case the final equation still has an e in it and will be this equation. For pressure, what happens for density? Well, for density we substitute again P by rho RT. So it means that we get rho 1 RT1 divided by rho 0 RT0, which is the same as P1 divided by P0, equals e to the minus G RT H1 minus H0. What happens now? Well, the R goes out, but the funny thing is that also this time the T goes out, which means that in the end the relation for density is the same as the one for pressure. So the equation becomes this one, which we already had for the pressure. So these are the equations for an isothermal layer, a layer with lapse rate 0, and that is a different set of equations, but not that different. We can use them in very much the same way. So let's summarize this and look at the total set of equations. For a layer with a lapse rate which is not equal to 0, so a temperature gradient layer, we use the equations on the left side of the screen. And on the right side, we have this set of equations where the lapse rate is 0, and this is what we call an isothermal layer, which means temperature is constant. So we have two sets of equations for different types of layers. Also be aware of how we use the indices. 0 does not mean sea level, but means the base of the layer. So only for the troposphere, 0 refers to sea level, but then it will always be the value at the bottom of the layer, the base of the layer. And 1 indicates the target altitude, and if we have to go through the complete layer to get to the next one, this might be the top of the layer, but if we need to be somewhere in a certain layer, then this is the target altitude. Also be aware of the units for lapse rate. It's in Kelvin per meters, not in Kelvin per kilometers. And this means that typical values are values like 0.0065 minus for the troposphere, or for the second layer in the stratosphere, plus 0.001. These are values in the correct units, Kelvin per meters. Never use a value like 6.5 Kelvin per kilometer. That is completely wrong and will get you very strange results. With these equations, we can calculate several examples, for instance, the Kittinger and the Baumgartner case. In the next video clip, I will calculate the pressure and density at the altitude of Joe Kittinger to see how close he really was to space. And then you can try later, as an example yourself, using the example of Kittinger, to do the same for Baumgartner and see how much he was in space and out of the atmosphere.